in order to substitute into equation 1, these two over here, equation 2 and 3, is pretty straightforward. You can substitute in there. But for these two, talking about velocity, I would need to differentiate this equation 1. So let me start by doing that, differentiating equation 1. I'm going to write a short form. This means differentiating. Differentiating equation 1. So that one will become theta naught t, and then c naught will be gone, so you have c1 plus, this is 2c2 t plus 3c3 t squared. I call this equation 6. I've seen exam scripts before that the student confused himself between this t and this plus. Right? Very subtle. It's two symbols over there, t and plus. Looks very similar, and what I did is to give it a little bit hook over here, so that as I do my checking, I can spot where are my t's. Seriously, if you miss out that t, you lose some marks. Just that, because it's wrong. Right? You will lose some marks. So please be careful. Every year I say this. Every year I get a few victims. So, this year, will that be you? Don't let that be you. Okay, let's substitute equation 2 over here into 1. Right, equation 2 into 1. So at time t I, that's equal to 0 seconds. My theta t I, we have seen before, that's equal to theta at time equal to 0. And we give it this angle theta I equal to c naught plus c1 at time 0 plus c2 at time 0 squared plus c3 at time 0 cubed. So you're going to solve that, and this will be gone, all this will be 0. So your c naught or your theta I is equal to c naught. So I've solved for one constant now. C naught is equal to theta I. The next thing is to substitute 3 into equation 1. So substituting that means theta tf is equal to theta f, theta I plus c1 tf plus c2 tf squared plus c3 tf cubed. And I call this equation 7. What I need to do next, I have solved for equation 6. I'm going to put in my velocity. So substituting equation 4 into equation 6. Right. So equation 4 is up there, where it says that my velocity at the initial time is equal to 0. So this one will be equal to 0. So that's 0 equal to c1 plus 2c2 at time equal to 0 plus 3c3 at time equal to 0 squared. So I can solve that. All this will be gone. I have c1 that's equal to 0. So c1 equal to 0. I'm going to put in here already. So this c1 is equal to 0. But later on I'll make use of this equation 7. Next, substitute equation 5 into 6. So where's equation 5 and 6? Equation 5, the final velocity is equal to 0. Substitute into the velocity equation 6. So if you're going to do that, final velocity is equal to 0 to c2 tf, because we don't know what is tf time, plus 3c3 tf squared. I call this equation 8. The next thing we're going to do is to do some assumptions. We're going to assume that theta I is equal to 0. Now, this part here, depending on the question, sometimes they say theta I is 30 degrees, then you put that as 30. But in my case over here, it's actually irrelevant where my starting point angle is going to be. I can start from 0, I can start from 10 or whatever. And then what I'm interested is after I started, what is my end position, what is the velocity and accelerations in between. So I can start from 0 just to simplify this case over here. So start from 0 angle, so 0 degree over here. And if I were to do that, my C naught will be equal to 0 because just now I solved for C naught over here and said that C naught is equal to theta I. So now if theta I is equal to 0, my C naught respectively will be equal to 0 as well. So let's look at equation 7. For equation 7, now it's a lot more simplified. Right? I have my theta F equal to, this is gone, this is also gone now, this is also 0. So I have C2 TF squared plus C3 TF squared cube. And I'm going to take from equation 8. So I have my C naught, C1 solved, C2 and C3 is not solved. So I take from equation 8. Equation 8 and multiply it by TF. Yeah? Multiply equation 8 by TF. So I have a 0 over here. I have this as 2C2 TF squared plus 3C3 TF cubed because I multiply it by TF. I also want to take equation 7 multiplied by 2 throughout so that I can then solve this simultaneous equation. Over the years, this simultaneous equation also collected some changes because for some reasons, some students find it hard, tough, right, how to solve for the unknowns. Simultaneous equation, I can't help you anymore. You must be able to solve simultaneous equation. Right? Later on, I'll put in some numbers and then I'll show you what happened. So this will be gone because you minus away from each other. So this will become 2 theta F equal to, this is 0, and then 2 minus 3 get minus C3 TF cubed. So I have one unknown here, C3, will be minus 2 theta F over TF cubed. So this is my C3. I have one more unknown, that's C2. So what I'll do is to substitute C3 into one of these equations. So if I were to do that, which one is better? Yeah, I'll just take any one. So if I were to substitute it into C3 into this equation, I'll get 2C2 TF equal to minus 3. Right, just bring it to the other side. And my C3 is minus 2 theta F TF cubed. And then TF cubed. Right, this can be simplified. Plus, minus and minus will become plus. Bring it to the other side for 2 TF. So C2 is equal to 3 theta. This 2 and this 2 can cancel off. 3 theta F divided by TF squared. Oh, there's a square missing here. I missed that out. Yeah, I was using this one over here. So C2, C3 now has been solved, and finally let's put everything together, all your solved coefficients, and I'm going to use red pen to tell you something that appeared in the exam in previous year, but no student know what's going on this year. polynomial position reference. So the question was asking you this thing. Solve for the polynomial position reference, and students who were looking just at the notes, it's not written in your notes. So they were left wondering, what is polynomial reference position? And some students raised up their hand, asked me, because I'll be there with you during the exam. I'll go to them and they ask me what is polynomial position reference, and I'll say, I cannot tell you that. Yeah, because it's today, here over here, right? If you miss that, then you're on your own. Okay? So please remember that. Polynomial position reference. What is that? That means this is asking you what is theta t with all your coefficients coming in. So your C0 and C1 will be 0. So C2, I'm going to use that 3 theta f divided by Tf squared. So please remember there's a T squared over there because this is your C2. And then C3 minus 2 theta f Tf cubed T cubed. So I can simplify this a little by bringing out the common factor of theta f T Tf squared. And I have 3 minus 2 T Tf. That is my polynomial position reference. So I've also seen before that students solve coefficients C0, C1, C2, C3, and did not write out the polynomial position reference, even though you're asked for it, you lose some marks. Right? Because marks will be allocated that. I've also seen before the other way around, that you are not asked to write down the polynomial position reference and the student wrote it down, you don't get extra marks. If you're not asked for that, just ask to solve all coefficients. So see what is it that you're being asked to solve your problem. Okay, now we are kind of like solving it in terms of variables, theta I and theta f. Let's have an example. Let's see. All right, this example over here. Okay. And it's a lot of words, so what I'm going to do is to do a sketch of that so that you'll be able to see what is that setup. Particularly in this question, you could see that it's saying using a third order polynomial for trajectory planning. That's where it's mentioned here. Sometimes it's not mentioned here. Sometimes not. But in this case, it's mentioned as third order polynomial. So I'll make use of that. So third order polynomial, how many boundary conditions are there? There'll be 4. So I'm going to list them all 4. It gave you this setup, y, x, and this lower link starts at an angle, and this angle, theta ti, where time gets started, and time gets started at 0 seconds. It gives you this as 30 degrees. And you also say that your theta dot at this time, initial time, I can do a shorthand writing in this way, is equal to 0 meters per second. Okay? But it is angle that is radians per second. So it moves, it starts with this initial position and then it moves to the next angle, right? Fanning out in that way. And this new angle over here, it has this theta at 5 seconds, right? You will take 5 seconds to move through, that's given in the question. And you'll move to a new position that's at 75 degrees. And you will end up with that velocity of at 5 seconds to be at 0 radians per second as well. So it starts at 0 velocity and ends at 0 velocity. So the question asks, can you find out what is theta at first second, second second, third second, and fourth second? That's what the question asks. So since there are 4 boundary conditions, so 4 boundary conditions, that's why we're using third order polynomial. So a third order polynomial will be using theta t equal to c0 plus c1t plus c2 t squared c3 t cubed. So let's start with the first boundary condition, theta at time equal to 0. Right? Theta at time equal to 0, all these terms here, t here would be 0. So you get c0. And theta 0 is at 30 degrees. So c0 is 30. Solved for one constant, one coefficient. How about the final? After 5 seconds, what is that position? I can substitute that inside here as well. So c0 plus 5 c1 plus 25 c2 plus 125 c3. This must be equal to 75 degrees. So c0, we have already seen that this is 30. Right? Later on, we'll try to make use of this to solve for the other unknowns. But for now, we just leave it as that 9. The other boundary conditions relates to the velocity, so we need to differentiate this equation over here. So differentiating that, I get theta dot t equal to c1 plus 2 c2 t plus 3 c3 t squared. So let's find out what is the initial velocity. Initial velocity is saying that this one must be equal to 0 at time equal to 0. So all this will be gone and you have c1 forward. And c1 is equal to 0. So that means this c1 over here, you can say that is 0. c0 over here is 30 degrees. So later on I'll make use of that. So there are only 2 more unknowns, c2 and c3. Putting theta dot for the velocity at 5 seconds. At 5 seconds, we were given that it is at 0 radians per second. So let's put it into this equation. You have c1 here as 0 already, so I'll leave it up. So the rest of it, 2 c2 at 5 seconds, 3 c3, 5 squared, that's 25, and it must be equal to 0. So now you have these 2 sets of equations. I'm going to tidy it up a bit. How am I going to do that? Is that I need to do simultaneous equation between this and that. So what I'm going to do is to multiply this by 5 and multiply this by 2 so that I can do my simultaneous equation. So multiplying by 5, knowing that this is 30 here. So I'll just tidy it up. I get 50 c2 plus 375 c3 equal to 0. Right, after tidying it up. And for this one is actually for this, right? This line here is for this. So the other one would be 50 c2 plus 250 c3 equal to 90. Right, so this is for that. That one is for this. Okay. And then we take the difference. C2, 50 minus 50, that will be gone. So you're left with this. That's 125. C3 minus 90. And then C3 equal to minus 0.72. So we could make use of C3 to solve for C2. Minus 75 minus 0.72 divided by 10. I get C2 as 5.4. So again, I'm going to use a red pen. They ask you to find polynomial position reference. So what that means is that can you put all your coefficients together? So C0 will be 30, C1 is 0, so C2 is 5.4 T squared. This is C3 0.72 T cubed. So that's polynomial position reference. If you're asked to find out what's the polynomial velocity reference, then theta dot T equal to, just differentiate that, you get 10.8, 2.16 T squared. If you're asked to find what is polynomial acceleration reference, then that's theta dot T, 10.8 minus 4.32 T. Just need to differentiate that. So it turned out that your acceleration is a linear equation.
Right. It's linear because I could see it's kind of like y is equal to mx plus c. Right. It's a linear equation. How about for your velocity? It's a quadratic equation. How about this? How do you call this? What sort of equation? T cubed. It's a cubic equation.
Right. So, but we haven't solved for what you asked for, which is theta 1, theta 2, theta 3, and theta 4. We want to find out what is the angle at time equal to 1 second, 2 seconds, 3, and 4 seconds. So what we need to do is just to take the position reference and put in 1 into t minus 0.72 equal to 34.68 degrees. Substitute 2 square minus 0.72 square cube. Solve for that, 45.84. I'll just do very quickly for the rest of it. That one will give me 59.16. And then for 4 seconds, 70.32 degrees. So if you come to here, then you get all your full marks. So I have tried to sketch out these few equations over here, your acceleration, your velocity, and your displacement. So if I do the sketch,
Right. So what I want you to see is that this arm was rotating, right? It started off at 30 degrees and then it rotates to 75 degrees. So that position that it moves has this sort of line over here. And this line is a cubic line. And as it moves across in that way, it has a respective velocity profile that is a quadratic equation. And then respectively, its acceleration is a linear line. So when you look at this, can you tell me if this linkage, is it accelerating or decelerating? It's decelerating. Right. So if you don't sketch it out, it's harder to see. But actually from the equation, if you look at your acceleration equation, it is minus acceleration is equal to 10.8 minus 4.32 t. That minus 4.32 would tell you that it's actually decelerating because of the minus sign. Right? So in your mind, you should have that clear, know that this is accelerating or decelerating. Okay.
Now what you have seen is a linkage that didn't really talk about the acceleration profile yet. So if I were to add two more boundary conditions to you, by saying initially it would have certain acceleration, and as it reaches the other position, the end position, it has another acceleration as well. So altogether, I'll give you 6 boundary conditions. 6 boundary conditions, how many number of order? 5th order. Right. So we're going to solve that. So that comes about. I just want to introduce to you how I did those plots that you saw. I picked it up. I did that online through this website. It's called FoodPlot, foodplot.com. Because not every one of you would have software to do the plots. So what I did is just go online, it's free, and then you can just do the plot to have a look at how the profile looks like. So this one here, the other example with acceleration limits. So with acceleration limits, what we're going to do is that we're going to assume the acceleration at the initial position at time equal to 0 to be 5 degrees per second squared. It can be degrees or it can be radians. So just now I was using radian. Probably I should use degrees per second here for the velocity. And for the final one, after 5 seconds, I'll say that it has this 5 degrees per second, minus 5 degrees per second squared. So now my acceleration profile is no longer a constant deceleration on the link. I define what sort of acceleration profile. You will start with 5 and you end with minus 5. So initially, you will try to accelerate, and then finally, as it reaches that final position, you will be decelerating. So these are the new ones. I'm going to write down the old ones. So previously, we have theta I that we solved, that's 30 degrees. Theta F, that's 75, that was given. Theta dot I, that's 0. I'm going to write in degrees now instead of radians. And theta dot F, that's also at 0 degrees per second. So this is a case for Ti equal to 0 seconds. This is a case where Tf is equal to 5 seconds. So previously all those conditions stayed. And now you have 6 boundary conditions. So we're going to deal with a fifth order polynomial. Let's have a look. Fifth order polynomial, I'll have 6 boundary conditions. So 6 unknowns can be solved for theta t. So for that, 6 boundary conditions, I'll have fifth order polynomial. So I'll write down that fifth order polynomial to be theta t equal to c naught c1t c2t squared c3t cubed c4t quart c5 t to the power 5. So fifth order polynomial, differentiate that because I would have to fill in those, I have to solve it using those boundary conditions. Differentiate that, I get c1 plus 2c2 t, 3c3 t squared, 4c4 t cubed, 5c5 t to the power 4. I'm also given the acceleration, so I'll differentiate the velocity one more time. 2c2, 6c3, 12c4, 20c5. So I'm not going to solve them step by step, but applying the boundary conditions. Solve for all the unknowns. I'll get C naught to be 30 degrees, C1 0, C2 2.5, C3 1.6, C4 minus 0.58, and C5 equals 0.0464. Alright, I didn't solve that. Every year, I always wonder when you get a 6 boundary conditions that you need to solve for 6 unknowns within the short period of time that's given to you in the exam. So far, I didn't see any 6 boundary conditions, but I'm not sure what will happen this year. I don't know. Because I haven't seen the exam question yet. It's not ready. Not yet. So again, I'm going to write down the polynomial, position, reference. By the way, robotics exam, year by year, we have a large number of A1s here, not A1s. We have a large number. Would that be you? Yeah, try to make that one for you, okay? So I'm going to put all the coefficients together. Theta t equal to 30 plus 2.5 t squared 1.6 t cubed minus 0.58 t4 plus 0.0464 t5. Okay, and it's just a polynomial position reference. If you're asked only for that, then you just need to write only that step. But I'm going to write now the polynomial velocity reference and polynomial acceleration reference. Very quickly, I'll just do that differentiation. And differentiate that again, we'll get 5. Okay. acceleration turned out to be a cubic equation.
How about for velocity? What kind of equation do we call this? Quadratic.
How about 4 to the power of 5? What sort of equation is that? We call it quintic. Yeah, not very important. I don't think we test it. It's just good to know that, you know, at higher order, yeah, there are names for them, yeah.
So what I've done is to do a plot of these few equations, because just now we saw that acceleration was a straight line, so it turned out to be a cubic. So I just want to see how all these lines would line up for my displacement, velocity, and acceleration. So it's also found in your set of rules here. So I just use that online software to do the plot, and I get this one. Yeah. So this is the one with the acceleration limits. And actually through here, what I want you to see is a few features that, especially for acceleration, because later on you get to hear, next class you get to hear about something about acceleration. Whenever you have the discontinuity in your acceleration profile, in next lesson you get to see that. Over here there's no discontinuity, it's a very smooth cubic line. If you have discontinuity, you experience jerk. And this jerk is bad for your robotic device, because your motor will experience that jerk. So as much as we could, we try to avoid that. So in this case, what is interesting is that your velocity can start from 0, but your acceleration has a certain value. And that is something great, even though the velocity is 0. So it's still possible here. Cases where you have 0 velocity does not mean that acceleration is 0, because it's impending to move already with that acceleration at that angle of 30 degrees. Same as the other side of it, you have this velocity coming to a 0, doesn't move, but it's impending deceleration. It's in an active zone that it has sudden deceleration. And the other interesting feature is that as it goes through this acceleration profile, you'll notice that there's one point there that has acceleration as 0. What does acceleration 0 means to you? Constant velocity. So at that point, you have this point over there that is considered a constant velocity, but over there is also your maximum velocity. So if you want to find out, as your arm moves, what is that maximum velocity, it will be when acceleration is equal to 0.
I think that brought us to the end of this thing, but it's not the end of the class. I want to touch on a little bit more so that next week we can dismiss class earlier, so we have time, right? So we cover a little bit more, next week we cover less. And actually next week there will be a staff coming in to do this lecture survey. And we'll end our class like 15 minutes earlier so that we can do the survey. So that's why I need to finish up this portion of it. Just a little bit more, yeah? Now you have seen before just now when I start talking about the arm
as it moves, there's this acceleration phase, and then this constant velocity, and then deceleration. So what I'm going to do next is to do a plot, and this plot would be of the axis of the position versus time. This axis as position. Position meaning theta, and then this axis is time. So in order for this to move through, the linkage arm to move through, we were talking about it needs to have this, what we call the acceleration phase, right? And then a constant velocity phase, and then the deceleration phase. So let me define this point. This one, later on I'll talk about that. I'll talk about this point first. So it starts off at this initial angle that's called theta I, and it will end at this point here that we also were talking about, that's theta F. So you will travel through with this part between point A and point B. This part between point A and point B is when the velocity is equal to a constant. So if I were to write it down, theta dot t is equal to a constant value that I call it omega. So omega is my constant velocity of this angular velocity, constant angular velocity of this plate. So this part here is accelerating, and that part there is decelerating. And actually, this kind of curve is a parabolic curve. This is parabolic, right? Parabolic shape. If you have not heard about parabolic before, no problem. I'll do a Google search image for you. Parabolic. Right. All these shapes, they are parabolic. Maybe I'll add in the word shape. Yeah. I'm trying to find one picture, but there isn't. So never mind. This is parabolic shape. Your quadratic curve, that is your parabolic shape. Yeah, what I was trying to find is a section of the curve. Okay, that's your parabolic shape. So these 2 points over here, there's actually a special word for them. They are called knot points. Why are they so special? That's because they are the transition from your acceleration to a constant velocity point. And that point, if not done properly, can you imagine something that's accelerating and then go into a constant velocity? If that transition is not done well, you'll get a jerk over there. Right? So what we'll be doing next week is to make sure that this point of acceleration can transit well into the constant velocity so that you wouldn't experience a jerk. So this part here, the time that it takes, I'm going to give it a few definitions. This is your TF over here. And at this point where it transits from acceleration to constant velocity, we call it TB. And TB is your blending time, right? You get to hear this word here, blending time. So whenever you hear blending time, that means it transits from
your acceleration to your constant velocity. The other point over here, that will be your TB minus, your TF minus your TB. Right, this point over here will be TF minus TB because we are assuming that your acceleration is the same as your deceleration. It's very seldom that you design your link to accelerate differently from deceleration. Yeah. Normally you design them to be the same. Okay? It's also easier for you. And normally we try to design it such that it can accelerate with the best acceleration that your motor could provide. Right? And later on I'll show you what do I mean by best acceleration. So there are a few more things. This time Ti over here is equal to 0, right, where it starts. This one over here, I call it theta B. This one over there, theta A. And at any time over here, at any time, I call this as time t, because it's at any time. Then at any time, that's theta I plus theta. Right? Theta I is over here. At any time later, it's just plus any other angle, theta. So these are my definitions. This theta I over here, the velocity will be equal to 0. Right? Normally we have your robotic arm in a rest position where velocity is equal to 0 before it starts to move. So normally that point would have 0 velocity. Now for the first parabolic theta t response, the, again, polynomial, I didn't use red, polynomial position reference equation is going to look like this. Theta t equal to C0 plus C1 T1 plus half C2 T squared. And that's about it. Second order polynomial. If you're wondering why is it that Dr. Tan didn't talk about anything about boundary conditions? No. That's because of something else. I want to bring you to acceleration. Alright. If I were to do all this differentiation, this will be C1, and this C2t, and this will be C2. Where I want this to be at constant acceleration. A constant acceleration here means that it's a 0 order polynomial. And what that means is that why my polynomial position reference is in such a strange with a half over here before I have a C2. That's because if I were to differentiate, I'll end up with a constant acceleration, which is what I wanted. So this half over here is so that theta dot dot t can become a constant after I differentiate it. And this, we stop at the second order polynomial. That's because we also want such that our acceleration will become a constant. This will be the first parabolic response. That means this part over here, the first parabolic response. Out of which there will be the following boundary conditions. For a second order polynomial, how many boundary conditions do you think we'll have? 3. So at Ti that's equal to 0 seconds, my theta at 0 time is theta I is equal to C naught, right? All this will be 0. Theta dot C1 will be equal to 0. Right? This will be equal to 0. And acceleration at 0 seconds, that will be C2, just a constant. So therefore, my parabolic section, the parabolic segment, have the form for 3 of them positions. You will have this form, theta I plus half C2 t squared. For your velocity, theta dot C2t. And for your acceleration, you will just have theta dot t equal to C2, just one constant. This constant is important because in the next class you'll see how we make use of this to blend into the constant velocity. Had it been not a constant for acceleration, you cannot blend into the constant velocity. So your acceleration must be not 0, but at least a constant, so that you can blend into your constant velocity. So I think I'll stop here so that next week we can continue. We'll have a look at how do we go about doing the blending. I'll see you next week.